Okay, the atom, we're talking about it, you know about it, this is what you know. Protons, neutrons, nucleus, electrons outside. Two models represented here. This first model, which model of the atom does that represent? Bohr's. So that's the old Bohr model. That's the one that you got familiar with in physical science. And then here, what do we have? What does that look like? It's fuzzy. That's on purpose.
It's the electron cloud.
It's the electron cloud. So this is really the sort of modern quantum model. I mean, I suppose you could call this like the Heisenberg and Schrödinger quantum model versus the Rutherford and Bohr planetary. But yeah, two models, both useful. So we're going to talk, initially we're going to start off talking here mostly about what's in the nucleus. Protons and neutrons, you know that protons have a positive charge, neutrons have no charge. They are electrically neutral. Protons have a mass of 1.673 times 10 to the negative 27th grams. That's tiny. Neutrons have a mass of 1.675 times 10 to the negative 27th grams. Are they identical? No. They're not. Neutrons are slightly heavier, actually. Are they really close? Yeah. You know, this is like the difference between 3,000,004 chocolate chips and 3,000,005 chocolate chips. Can you tell them apart? No. You can't. So here's the weird part. If we put two things that are positively charged together, what do we expect them to do? Like charges repel. So we've got these protons that are all clustered in the nucleus. And we would expect them to be repelled by one another, but there are these things called nuclear forces, and there are actually strong and weak nuclear forces. There are two of the four fundamental forces of the universe. They just are. It's one of those things. Unless you're a crazy physics person, you don't question that much. They just are. So, oddly enough, protons are actually attracted into the nucleus by these nuclear forces. You know that atoms are tiny. We measure them in picometers, and the nucleus of an atom is about 1,000th of a picometer. Remember that a picometer is already 10 to the negative 12th meters. This is tiny little scales that we can't even conceive of. Okay, so now we get into things that are sort of more observable. Atomic mass. So atomic mass is equal to the number of protons plus the number of neutrons. That's easy. An atomic mass is measured, because science people are creative, in atomic mass units. Very creative. So the AMU with which we measure atomic mass, what is the unit for atomic mass? Why, it's the atomic mass unit. It sounds rather circular. It kind of is. We noted that protons and neutrons aren't exactly equal in mass, but they're so close that it's indistinguishable to us, to mere mortals at this scale. So what we do is we say that one proton or one neutron is equal to one atomic mass unit. So the mass of a single proton is 1 AMU. The mass of a single neutron is 1 AMU. Okay, so how many of you have heard the word isotope before ever? Okay. How many of you remember what it means without reading the slide? Okay, that's fine. Not all atoms of a given element are identical. That's one of the things in which Dalton was incorrect. He didn't know this. So you can have 3 different atoms of carbon that have slightly different masses. Those are all isotopes of carbon. So isotopes are just atoms of an element that have the same number of protons, because this is what defines the element. So I'm going to make a note here. Oh, it's frozen again. but they have a different number of neutrons, which gives them a different mass. So if we subtract from their mass number their atomic number, what we get is the number of neutrons. Because the mass number is equal to protons plus neutrons, where the atomic number, so the mass is equal to the protons plus the neutrons, where atomic number is just equal to number of protons. We name isotopes based on their mass. One of my favorite who's buried in Grant's tomb kind of questions. I will at some point ask you, what is the mass of uranium-238? Guess what the mass of uranium-238 is? 238. Guess what the mass of nitrogen-14 is? 14. What is the mass of cobalt-60? 60. The mass of potassium-40? 40! You guys are getting this. This is good. I call them Grant's tomb. Are you familiar with who's buried in Grant's tomb? Grant. So I call these Grant's tomb kind of questions, like, what's the mass of carbon-14? 14! Yeah. I will ask you that on a test, and I have had students get it wrong, so I'm telling you now, if I ask you what the mass of an isotope is, we name the isotopes for their mass. Please don't miss it. I'll cry. I'll cry. I could devote this entire page to questions like, what is the atomic mass of hydrogen-3? 3. But I think we'll just talk about how to write isotopes, because I think you get the atomic mass thing, right? Okay, so when we write the name of an isotope, there are two different ways to represent it. The basic two methods are hyphen notation and symbol notation. Again, man, these are easy. Guess what hyphen notation has? A hyphen. Symbol notation uses as its base the atomic symbol. Now, don't get confused, because we can also do sort of shorthand hyphen notation and use the symbol with a hyphen, but that's just still hyphen notation. So, how would you write? We're going to practice writing some isotopes, but first I want to talk with you a little bit about this periodic table. This is the Van Braner periodic table. This is one of many periodic tables that you will receive from me. And I also gave it to you electronically. So, anyway, the Van Braner periodic table is really nice. It was laid out by S.E. Van Braner, who, I can't remember where he teaches. He's a chemistry prof someplace. And one of the things I like about it is it doesn't have the names of the elements on it. You'll notice it's just got the symbols. This is his simplest version. It's just got the symbol, atomic number, atomic mass. We'll use some that have a little bit more information on them later. I don't expect you to memorize the periodic table. I think that's silly. You are going to use it so much in this room that you're going to memorize it anyway. And while I don't expect you to, I'm not going to give you a test over memorizing it, I'm going to use the symbols assuming you know what they mean. Basically after this unit, I will assume that if I say C, you know I'm talking about carbon. If I say Na, you'll know that's sodium. And really, the ones that we use commonly, you're going to have memorized by Christmas. You just will, because you'll use them so much. All right, so we've got the periodic table. You're going to be using the Van Braner a lot. I gave this to you electronically because here's the other thing you can do. You can make that PDF a background in your dossier. Here's where I did a custom background with the Van Braner periodic table. And if you're doing anything with this area, we're using the periodic table a lot, it's kind of nice to have this. So you've got it electronically. You can use it that way. I also just gave you a paper copy. It's the first of many, many, many paper copies of the Van Brainer that I will give you with different purposes. So let's do a little bit of practice. How would you write, using your periodic table, the hyphen notation for sodium-23? Do you have one of these two? It's coming. And because I didn't specify, shortened hyphen notation or full hyphen notation, either one of those is acceptable. Either one of those is correct. If you're writing something to a chemist is going to know what either of those means. They're going to know what you're talking about. So go ahead and do the hyphen notation for boron 11. Okay, you should have something that looks like one of these. Now, these are easy. Everybody gets the hyphen notation correct. The one that people do tend to screw up, and I'll tell you where they screw it up, is the symbol notation. Go ahead and do symbol notation for sodium-23. And of course, what you're remembering is that the mass goes up top. And my mnemonic for remembering that is that when we're talking about isotopes, mass is the most important thing. It comes first. Because we know it's carbon, we know it has 6 protons. That's less important. So on the top is always going to be your mass. For grins and giggles, go ahead and do the hyphen or the symbol notation for boron 11. Okay, you've got boron with an 11 and a 5. Pretty easy to understand, pretty straightforward. You're never going to miss a problem when I ask you what's the mass of boron 11. Right? Yes. So, now let's get into the slightly more, I'd say, interesting, the slightly more complicated part about atomic mass. Okay. In honor of the current events, recent events in Cleveland, we have a half a baseball here. Can we have a half an atom of carbon? Not and still have carbon. If we take a half an atom of carbon, we have lithium. Matter of fact. 3 protons, 6 protons. So then look at the atomic masses on that nice periodic table that I gave you. What's the atomic mass of, well, let's say carbon? 12.0107. How can we have 0.107 of a carbon atom? Can we have that? If we can't have that, then how is that the atomic mass? Look at Look at chlorine. It's atomic number 17. What's the atomic mass of chlorine?
35.4527.
Yeah, 35.4527. It's like 35 and a half almost. How can you have an atomic mass that's 0.45? How is that possible if we can't have a half an atom of something? We can't have, I mean, we said that these are actually the numbers of protons and neutrons. Can you really, what you're looking at is a half a proton or a half a neutron. Is that possible? Can you have a half a proton? Half a neutron? Well, then what's up with this? Grr! Is this legal? Is this even legal? Does anybody actually know the explanation?
Do they calculate in the mass of the electrons too?
They don't. That's a great hypothesis. What would be some other possible explanations? So we said that electrons have this little teeny tiny mass. It's like what, an 800th of a 8,000th of a no, a thousandth of a hydrogen atom. So maybe this includes the electrons. Okay. What's another possible explanation?
Well, the masses of protons and neutrons aren't whole numbers.
Okay, but we said, and okay, so that's possible. So maybe this gets back to, well, we said we were just going to call them an AMU, but we lied. That's a possible explanation. What are some other possible explanations? Should we contact the International Union of Periodical and Analytical Chemists and alert them to this? Perhaps they're not aware. Get UN peacekeepers involved. UN chem keepers. No. What would explain this? So yeah, if we're counting in masses of electrons, that would explain it. If maybe we're not really making them just one AMU, we're actually saying, oh, well, this one's 0.99 AMUs and this one's 0.97 AMUs. But I can tell you that neither of those is the case. What did we just finish talking about? Isotopes. What's an isotope? Very good. You can read. Yeah. They have different masses. They have different masses. So, how do we account for having a single atomic mass if some elements of carbon have a mass of 12 and some have a mass of 13 and some have a mass of 14? How do we get a single atomic mass to put on the periodic table? Oh, yeah. Well, matter of fact. Well, close. They're weighted averages. This is also how your chemistry grade is calculated, so it's a nice thing for you to pay attention to. I will teach you how to do weighted averages, and you can calculate your own darn chem grades. Okay, you have progress book to look at home. Usually, and the thing that I think you're taught as freshmen is round to the nearest whole number. Is that what you guys were taught? Just round it. Makes me crazy. The nearest whole number usually is the most common isotope. It's not 100% foolproof. There are cases where, the two most common isotopes are 56 and 58. And when you average the masses, you get 57.3. Well, no, 57 is not the most common isotope. But in general, we can take a good guess that if we look at the average atomic mass, the nearest whole number is probably the nearest isotope. There are, like I said, a few exceptions. But what we're going to do is actually look at calculating an average atomic mass. And I have a little analogy to share with you. But first, let's just quickly look at some atomic masses and practice taking a wild swing at what the most common isotope probably is. Okay, so if I look at, well, I'll look at fluorine, atomic number 9, and you've got that on your Van Brainer periodic table. If you had to take a wild flying guess, somebody who is wearing black or gray, who I have not heard from yet today, what would you expect the most common isotope of fluorine to be? Black or gray, anywhere on your body? Got lots of black and gray there, buddy. Yeah, so fluorine 19 we would guess to be the most common isotope of fluorine. Okay, what about iodine? I can't get out of the halogens today. Atomic number 53. What would you expect to be the most common isotope of iodine? Iodine 127. And I think it's iodine 128 is a radioactive isotope of iodine, I believe. Okay, what about aluminum? Al, atomic number 13. So the most common isotope of aluminum is probably aluminum 27. What about cobalt? Atomic number 27. Right there. Part of the magnetic triad. Okay, somebody without laces in their shoes. With no laces. And actually, it strikes me, so cobalt 59 seems like a very reasonable guess. Something rings, I know there's a cobalt 60, which is a radioactive cobalt. And I'm not sure cobalt isn't one of those weird ones where we would look at it and go, probably 59, and it might be like 58 and 60 or something. But I could be wrong. One other thing to just be aware of, whoops, I got to take, you may sometimes also see the word nuclide, and if you're going on in chemistry, you'll see this sometimes. It just is addressing all the possible nuclides of an element. You'd be talking about all of its isotopes. So I think we're not going to have time to do a practice problem on this, so we will pick up on Tuesday with weighted averages. Actually, no, here's what I'll do. I'll have a tutorial on weighted averages for you to watch on Monday, and then you'll have some assigned practice problems. So that's where we'll leave it.